Okay, so welcome everyone to our OpenSim webinar. My name is Jennifer Hicks. I'm the OpenSim Research and Development Manager here at Stanford, and I'll be serving as the moderator for the webinar today. And I'm pleased to welcome today's presenters, Fregly and Carolynn Patten, who are joining us virtually from the University of Florida. Can you go ahead and advance to the next slide, BJ?
There you go.
There we go. So the key goal of our webinar series is to showcase cutting-edge research that's applying modeling and simulation to solve biomechanics and rehabilitation research problems, which is why we've invited Dr. Fregly and Dr. Patten this morning. OpenSim is also a growing and geographically diverse community of users. So the second goal of our webinar series is to provide a platform for the OpenSim community to communicate and collaborate. So it's exciting that BJ and Carolynn have agreed to be our second set of external speakers helping to build this community. Before we get started, I have a few reminders about the webinar format. First, questions will be addressed at the end of the presentation using the Q&A panel, which you can find on your WebEx Event Center. And if you need any additional technical help, you can consult the webinar guide that's on our website. So let's go ahead and get to the talk. BJ Fregly is a professor at the University of Florida who's been closely involved with the OpenSim project since its beginning. He serves as a member of our Symbios Scientific Advisory Board, and he's been helping to build a modeling and simulation community by running the annual Grand Challenge for predicting knee loads, which I think is the first of its kind in the biomechanics community. Our second speaker is Carolynn Patten, who is in the physical therapy department at University of Florida. She has a vast clinical background that includes neural control, physiology, and clinical rehab. And these two researchers, they've been combining their modeling and clinical expertise to improve the rehabilitation of stroke patients, which is what they're going to discuss with us today. So again, BJ, Carolynn, thank you, and I'll let you take over now.
Great. Thanks, Jen. All right, so I'll start off by giving everyone an outline for what we're going to present today. So we're going to start out by talking about building not just a clinical modeling collaboration, but building a healthy clinical modeling collaboration, which isn't necessarily an easy thing to do. Then we'll spend some time discussing a clinical problem description, which Carolynn will give us. Then we'll talk about a modeling technology description, so how we'll use modeling, hopefully, to address some of these issues. Then we'll talk about how some of the modeling technology that I'll be presenting can potentially be implemented in OpenSim. And finally, we'll draw some conclusions. So first, I want to talk about building a healthy clinical modeling collaboration. So we believe that improved collaboration between clinicians and modelers could lead to improved treatments for gait-related disorders. But I want you to consider the following 5 possible approaches for building a clinical modeling collaboration, because it's not necessarily something that's easy to do. So here we have a sandbox with 2 individuals in it. The one on one side is the clinician there, and the one on the other side is the modeler. And the first approach that we can have to a clinical modeling collaboration is where the clinician says to the modeler, I don't need modeling capabilities, which is like saying, why are you in my sandbox? And so the issue here is that we sometimes have no intellectual interest from the clinical side. Second approach is where the modeler says to the clinician, I don't need clinical applications. So the analogy there is, why are you in my sandbox? And so we can also have modelers who have no intellectual interest in the clinical side. Third approach, starting to go in the right direction at least a little bit, is the clinician is now interested in, or excuse me, the clinician is now interested in having the modeler get involved and says, come work on my clinical problem. So that's a good start. But that's really saying, come build in my sandbox. And the issue we have there is that the intellectual investment and ownership come primarily only from one side, the clinical side. So as you might guess, the fourth approach is the reverse of that, where the modeler says to the clinician, come use my models, or come build in my sandbox. And so here we have the issue that the intellectual investment and ownership come primarily from the modeling side. And so all these approaches are suboptimal. What we really want is approach 5, and you can now see that we have smiley faces on the clinician and modeler. And here they say to each other, how could modeling help clinical problems? Or let's build in the sandbox together. And what's different about this approach is that now we have shared intellectual investment and ownership that comes from both sides of the problem. So one caveat that we want to give today in this shared investment approach to addressing stroke rehabilitation is that our presentation is going to be more of a vision for where we hope to go in the future than a completed story for what we've already achieved. So this is work that is under construction.
Thanks, BJ. So I'm going to talk a little bit about the clinical problem and the describe the clinical program that I have going on and how I've come to engage in an intellectual interest in a modeling approach. And BJ reminds me we need to discuss how we got this far, and we had a unique opportunity that deans of our respective colleges here at Florida locked us in a conference room and said, how can you guys figure out a way to play together? And out of that meeting, which involved maybe 30 people, I think that BJ and I are the only who have continued with a productive collaboration. In truth, there was a series of events, some on each of our sides, and one on my part was certainly an evolution of my research program where I'm looking at neuromechanics in a clinical population, but it comes to a point I need to ask questions on a larger scale, and that BJ's modeling had developed to a place that he wanted to expand questions as well. So in terms of the clinical problem looking at stroke, this is a very high-level view of the big picture, or sort of what I would say the so what, who cares part of it. Worldwide, we look at a problem of 16 million people who experience a stroke, and there are now 23 million survivors of stroke because there have been tremendous advances in the acute and hyperacute care in medicine. So it used to be that we would look at this being tremendously disabling and people being essentially not capable of gaining recovery and mobility, and it being a very poor prognosis for their participation in life. Now it's so much better that once they navigate the acute medical events, they experience a fairly normal lifestyle. And part of what is critical, it's been a notable change, is there's an increased incidence of stroke in what we used to call young stroke, or people in their middle age or in the working years of their lives. And this ends up being very, very important when we think about people who want to participate, go back to work, raise their children, enjoy all of the things that we take for granted as normally mobile people, and not necessarily wanting to be ridden to wheelchairs or braces or assistive devices that, depending on that for mobility. This is just a quick comment from the World Stroke Organization. They are on an international campaign that they refer to as 1 in 6, to remind us that it's actually 1 in 6 people worldwide who will experience a stroke, and that is actually a stroke that occurs someplace in the world every 6 years. Where I'm going with this is that this is a big problem. So it's worth our time and it's worth our effort to see if we can't use our intellectual tools to come up with better outcomes for these individuals. On the rehab side, the focus of rehabilitation for decades has been palliative care or compensatory approaches to rehabilitation, and really the anticipation that these people would not have much of an active participation in life. And of course, with this increased incidence in the younger age ranges, we need to change our focus to the terminology that's used in the rehab community is to recovery-based approaches to rehabilitation. And this is actually a paradigm shift, because I think many people in medicine still think once a stroke has been experienced, the capacity for recovery in the nervous system is quite limited. And the conversation that's on the cutting edge is, how do we promote restoration? What is the capacity for recovery? Just a few quick comments, and I will not dwell on these, but what is, for those of you who may not engage in this type of conversation regularly, what does rehabilitation for stroke look like? And I'll just headline this with saying we really haven't cracked the code. In clinic-based settings, theoretically, a lot of places, they will engage in an approach that is called motor learning, or drawing on principles of motor learning. So similar to the approaches for gaining motor skills in development or for sports, the therapists in rehab settings would try to apply these skills to people who had had a stroke. Another approach that is quite large here in North America and has had a lot of engagement in research recently is locomotor training. The argument for locomotor training is it is task specific. The idea here being that people train to practice the whole task of walking, which includes standing upright, reciprocal stepping, bearing weight, engaging in transferring weight from one limb to another. And we'll get onto this in just a little bit more. A lot of places will simply have people walk on a treadmill and use that as a way to get in repetitive practice of walking. There are still a number of people who are interested in using FES, functional electrical stimulation, and there's an industry behind stimulators, wearable stimulators, to trigger activity in the dorsiflexors to counteract foot drop, and people, purportedly to help them aid them in clearing their limb during swing phase of gait. There's also some interest in, there's actually quite a lot of interest in various forms of robotic devices, the idea being that robots could help with the labor-intensive aspect of giving tremendous number of repetitions and practice that are required to drive neuroplasticity, and neuroplasticity being the physiologic premise that underlies recovery of function. And a subset of these robots could be considered exoskeleton robots that are wearable and allow people to engage in more normal environmental situations. And finally, ideas that are really quite contemporary being explored in a number of ways are extrinsic forms of neuromodulation. These include repetitive transcranial magnetic stimulation, the idea there being that it's stimulation that can actually change the excitability of the motor cortex. There are various ways and approaches to delivering repetitive TMS, and TDCS is transcranial direct current stimulation, which is a low intensity stimulation. And the advantages to TDCS is that they can be delivered online, which means that while people are actually engaging in physical activity, like walking, one of the things that we're interested in doing. So just quickly, some pictures, some ideas. Early version of walking robots are this mechanized gait trainer that was developed by Hesse and colleagues in Germany. And the fundamental principles here were just to get people standing upright, stepping reciprocally. There was some balance. They would wear, there was some external stability for balance. They would wear a harness to partially offload body weight. But notably, the foot stays in contact with the foot plate, and so they never are engaging in an open kinematic chain. These are examples of more typically used body weight support systems. Brand of one of them, or both of them, are the light gait, can be brought up over a treadmill, can be used over the floor. And the idea here, again, is just to partially offload body weight, which could help. Maybe some people use it just for balance, to help people regain balance. Other people use it specifically to say we want to reduce a specific percentage of their body weight. The Locomat is an example of one of the robots that's used. It's an exoskeleton that is actuated at the hip and the knee, helps the participant to engage in a reciprocal stepping pattern, bilaterally symmetrical. Lots of debate about the controller systems. Are they passive? Are they feedback controlled? Should they be done differently? But essentially at this point, the evidence suggests if you have somebody train in a Locomat, or you have them trained with a therapist and hands-on in a partial body weight support system, everybody gets a little bit better without a notable difference between the two different forms of this locomotor training. These are examples of a variety of exoskeletons and being developed, Berkeley Bionics, Tibion, University of Michigan, and each has their their own approach of whether they're trying to help with weight bearing, actuate through pneumatic assistance to provide additional force production. But in general, the argument in favor of these is that it allows people to get out of the clinic. They can go outside, they can navigate uneven terrain, they can walk up and down stairs, and these are, in fact, the locomotor problems that people need to solve in the real world. A few words on outcomes in rehabilitation. This is always a difficult conversation for me. I am very much of two minds. I'm a very cynical clinician, so I will describe what's used in the regular clinical world, but to the biomechanical community, you'll sort of say, what? You know, in this case. But when we look at clinical outcomes, the results end up being there is some improvement in walking function. The effects are very small, partially, I think, because of the measurements that are done, the measurement tools that are used, and a lot because of the heterogeneity, both of the patient population and of the interventions that are evaluated. Most commonly, the most common outcome measure used is gait speed, just overground gait speed, or a timed walk, a 6-minute timed walk, or a 10-minute timed walk, and these are generally done just on level ground and most typically done inside. Now, there are a couple of notable exceptions in the literature to these very modest outcomes, and one of these is work that is emerging from the lab of McCain at University of Texas Southwestern, who has published a couple of remarkable small studies where people post-stroke regain essentially normal walking function at six or 9 months post-event. And by normal walking function, I mean these are people who can walk without a brace. I think of her, she's probably reported results on 20 to 30 people at this point, with only a few of them still requiring a straight cane at 6 months. And in many cases, she doesn't always have kinematic data, but some of her kinematic data show that there is actual symmetry in the joint angles between the predic and the non-predic limb at 6 months. And this, to my knowledge, she is the only person who has demonstrated this, at least in the literature. The other remarkable case are data that emerged from Marcus Pohl in Germany, and had a rather large sample size with his primary outcome being fast walking speed. And he took a very aggressive approach to rehab, essentially used an interval-based training with the idea being, you know, we need to challenge people with stroke just as we would challenge ourselves, or we would challenge athletes to walk faster or to run faster. And indeed, his data show that people post-stroke can regain relatively normal walking speed and fast walking speeds, you know, approaching normal individuals. The limitation, I have to discuss this with a caveat that the limitation in the publication is walking speed and perhaps some spatial temporal parameters, and I can't really comment on what the joint angles and the biomechanics look like in this case. But these two studies give us evidence that it is possible to do better than what is generally reported in the rehab outcome, and it's possible to do far better than what our expectation has become over the last several decades of stroke rehab intervention research. I'm going to talk for a little bit about some research that's come from my lab, and this is actually the test bed and the inspiration for the work that DJ and I are doing together. So just quickly, I too, I have a horse in the race, if you will. I conducted a small clinical study, 36 people post-stroke, and they were between 6 and 18 months post-event, and they enrolled in a staged intervention. So in stage 1 for 5 weeks, they had large power training. We delivered power training to the predic limb, multiple joint actions, and then they were reevaluated, and then they moved on to 3 weeks of clinic-based gait training. So this is a therapist one-on-one with a participant doing tasks more like the motor learning approach, which the first of the approaches that I described. Our primary outcome was self-selected walking speed, and this done, again, I'm of two minds in saying this, but if you are talking in a clinical world, this is what they want to hear about, and it's referred to as a primary outcome. So if we measure their self-selected walking speed at the end of the first phase, there was a significant improvement. This is in all 36 participants. In the second phase, there was an increment, did not reach statistical significance, but overall, at the end of the 8-week intervention, there was indeed a significant improvement in their walking speed. Now, when we find our way through the data, the far more interesting story that emerges is that the group sorted themselves into two subgroups that we refer to, not surprisingly, as responders and non-responders. I'm illustrating that here in the blue group and the red group, and the yellow shaded area behind the red group is showing what we refer to as a minimal important difference. And so statistically, clinically, one of the ways that data are often analyzed is to say, well, what is the mean of the sample at baseline? What is the variability of that sample at baseline? And based on those data, or based on those measurements, to determine what is a change that would exceed the variability of baseline. And so that's what is exhibited here in this yellow shaded area. And our point being that the non-responders did not emerge from the measurement variability, but in fact the responders did at both phases of the treatment. Now, I'm going to sidestep for a moment and talk about another study, and this is from the literature. This has been published in the Journal of the American Medical Association, a large multi-site clinical trial of locomotor training. And so locomotor training is another one of the interventions that I described in my overview, and the critical ingredients of locomotor training are argued to be have somebody step on a treadmill, they have partial body weight support, and they are assisted by therapists to gain a normal, reciprocal, symmetrical, bilateral pattern. And again, I refer to this in quotes as this is argued to be a task-specific approach to regaining locomotive function. So the LEAPS trial was, again, this is by clinical standards. The gold standard is a multi-site clinical trial, controlled clinical trial. And so what that means is you have people from different parts of the country, so different demographic representation. You have lots of participants, so the variability in the clinical presentation and also the socioeconomic, other forms of demographics that can contribute variability. And in my mind, something that's equally important is that at multiple sites, therapists would all be delivering interventions, but you have more than one therapist giving that intervention. So a little bit earlier, I talked about the work coming from McCain, from Patty McCain. She has produced some phenomenal results, but so far they come from her. And so that's one person doing it, doing a really, really good job. But in the end, if we're really going to help people, and this is going to generalize to a lot of people, any clinician in rehab, it has to be accessible to them. They have to be able to understand how to administer and how to elicit this type of result. So this is one of the critical ingredients of a multi-site trial and what was being examined in LEAPS. So 400 people enrolled, and the question was, is locomotor training, the hypothesis was that locomotor training would produce better walking outcomes at the end of a year, 1 year post-stroke, than a one-on-one program of therapy delivered by a therapist in the home. This is not like just, if any of you have ever had therapy for a sports injury or a back injury or something like that, it's not uncommon that you might be given a home exercise program to reinforce and follow up what's being done. Instead, in LEAPS, the alternate treatment involved a therapist going to the participant's home and delivering a tailored therapy that involved balance and strengthening and walking, but no extra equipment, being the part of this. Okay, well, I've given the punchline here. At the end of a year and 400 people later, 400 participants later, there were no differences between the treatments. And equally impressive was that the change in walking speed, this is overground walking speed, was on the range of 0.23 to 0.24 meters per second. They asked an additional question: what if you got locomotor training early, within a month following your stroke, or later, following 6 months of your stroke? And it turns out that the late group got the same total increment, with that being broken into about half what they got in when they were out on their own, and then the second half they got when they were actually getting the locomotor training therapy. Okay, so the thing to take from here is this idea of the task specificity of locomotor training certainly drawn into question. And something, another way that I put it often is, it looks to me that there is what I would call a robust biological effect. Here in Leeds, 400 people, 3 different sites around the country. At the end of a year, they walk about 0.24 meters per second faster. Interestingly, now we're slipping back to data from Matlab, a humble number of 35 people, not nearly as grand of expectations, but what we find here in the shaded area is a change in gait speed of 0.23 meters per second. So we had our responder group exceeded, or let's just say that they met that same increment as the average group from the Leeds trial. And what I'm saying here by robust biological effects is that it seems like it may be the case that whatever we do, that might be what we can get with our current understanding of rehabilitation. It doesn't really tell us, first of all, it doesn't really get us back to normal walking speed. This is, I referenced 1.2 meters per second as being about normal walking speed. So even though our responders showed a statistical improvement, they're still quite a far distance from a normal walking speed. And our current therapies don't really seem to be probing that, don't even seem to be asking that question, can we get people back to this level? Okay. Another piece of the puzzle is the ability to predict who might be a responder and who might not be a responder. And so clinically, we can look through these things. Well, what about the severity of their stroke? You know, common sense would just say, oh, the worse their stroke is, the less likely they would be to recover. Turns out that their baseline severity was not a predictor. What about where the lesion is? Again, common sense would say, well, if you have a stroke in this part of the brain or that part of the brain, you know, there are things that are known about, you know, the capacity to recover. Certainly, if we're talking about speech function, cognitive function, I think less is known about walking function. But in our case, in our 35 people, lesion location was not a predictor of who would be a responder or a non-responder. And yet another piece that is common sense, you would think, well, the time post-stroke would be important. And I think that is true if we're talking about people who are 1 month post-stroke or 5 years post-stroke. We certainly would expect that the people who are closer to their stroke would recover better. But in the data I'm describing from my lab, everyone is between 6 and 18 months post-stroke. But even given that variability, we did not find a difference between the 6-month or the 18-month people. We had some experimental factors as well. We took baseline walking speed, overground walking speed, asked the question if it predicted who would recover. It did not. May just ask you to recall the picture you can from the plot I showed a couple of slides ago, and all of the walking speeds actually clustered quite tightly together at baseline. So we didn't find that there was any predictive value in their baseline walking speed. And we had some group randomization, based on who got what form of treatment in these different phases, and it turns out that did not contribute to our responder non-responder story either. At the end of the day, we have 4 patterns that emerge in these 35 people. Non-responders, so these are being illustrated here in the red bars, and they got small incremental changes in gait speed, but none of them reached what we call this magical clinically important difference. The second pattern of responders are people who actually did not improve to the lower, in response to the lower extremity power training, but when they moved on to the clinic-based gait training, got significant improvements. And you can see that there's just like a step function there. The third group of responders responded, it's almost the reverse of what I just described. They got their improvements in response to the power training, and then tailed off, plateaued or tailed off a little bit in response to the clinic-based gait training. And our last group are what we call the incremental responders. So they just showed increments in response to both interventions. And the obvious question there is, why did you stop there? Would they have continued if you had done more? And that certainly is a question that's waiting to be answered. So we're going to switch back to BJ here in a minute, but the point being, we have these data. We have this large, very, very rich data set of 35 people. When I look at it through the lens of the clinical trial, or the way that the clinical world wants to hear about it, I really come up with very unsatisfying answers. Yes, people walked a little bit faster. We don't know why. We don't know who. And back to touching on our public health type of message, it would be really important information to understand a priori who's going to be a responder, who's not going to be a responder. It has huge implications for healthcare if we can make those decisions in advance. Another corollary to that are the questions of who is really getting recovery in terms of, are they regaining normal mechanisms of gait and control of their gait, versus people who may be walking faster through any means possible and demonstrating a markedly compensatory gait pattern. So I don't need to tell this audience, but you don't get that information when you're measuring your primary outcome is simply walking speed. And so we have instrumented data in all of these people and have then this unique opportunity, since we know we have these two patterns of responders and non-responders, to go backwards and say, what can we get from modeling? What can we predict from a model in the baseline data, who would be a responder and non-responder? And I think that BJ is also anxious for the opportunity to say, well, what if we manipulate the model, and can we make some predictions of what's possible from there? So I'm going to pass over to him.
Great. Thanks, Carolynn. So Carolynn's done a nice job of showing us these differences in treatment response between these two groups, and then even within the responder group, we have some differences in how people respond. And we also saw from Carolynn's portion of the presentation that it looks like there's a lot more potential that remains untapped in optimizing rehabilitation for these individuals. So the objective of the modeling part that I'll present is trying to predict the theoretically best, where by best we mean the fastest and most symmetric walking pattern that an individual can achieve post-stroke. Because if we can predict how well a person can do and how they would do it, we may be able to categorize them as a responder or a non-responder, as a particular type of responder, and so that may help us to be able to customize the intervention to the individual and do the intervention in the most effective way possible. The approach that we're going to follow for trying to do this is optimization of patient-specific walking models, and these models will be unique in that they'll account for each patient's neural control limitations and remaining capabilities, and I'll talk about that more shortly. And the rationale here is that patients may not naturally be finding their best achievable walking patterns, and I liken that to athletes who don't naturally find their optimal movement patterns without appropriate training. So maybe with appropriate training, individuals who have had a stroke can do a lot better as well. So in order to go down this path, we need some computational resources that we're going to pull out of our computational toolbox. And some of these resources are existing. We need to be able to do predictive gait optimizations to predict new walking patterns. And we're going to have to use something called muscle synergy analysis, which is going to provide some constraints on the achievable muscle excitation patterns that individuals can achieve. And we're also going to need some new elements that are missing right now. We're going to need something called statistical moment estimation, which is a new way of turning processed EMG signals directly into joint moments. And we're going to need some customized ground contact modeling to describe how an individual's foot interacts with the ground during walking. And then finally, we'll have to integrate those 4 different areas together to come up with a computational framework where we can predict new walking motions that will hopefully be indicative of the best achievable walking motion that an individual can produce who's had a stroke. So as we go down this path, it's helpful to think about how this path might be different than what the traditional approach would be today. So if you want to have a muscle-driven simulation or optimization of walking today, what you would normally do is you would take either some experimental processed EMG data, or maybe you would predict some muscle excitation patterns with an optimization. You'd put those straight into a musculoskeletal model, and then you would drive the muscles directly with those excitation patterns. You may put experimental ground reaction forces in at the feet, or maybe you would have some simple foot-ground contact model, but it wouldn't be customized to the individual. So here's what we're proposing to do, and you can see there are some new elements to what we have here. So I'll focus this in on the top here. So first of all, we're still going to have muscle excitations that go into the model, but we're going to add a layer above where we're going to have a subset of commands that are going to be used to control a larger number of muscle excitations. So this is where the muscle synergies idea will come in. I'll talk about this more in a second to explain that better. And then we're going to eliminate muscle models and all the parameter values associated with those. And instead, we're going to go right from our muscle excitations in the model directly to joint moments that are going to be driving the model. So this reduces a lot of the complexity in the model, and we'll show shortly how we're going to do that. And then finally, we want to have customized foot-ground contact models that can model the foot interaction of individual subjects, because we want to make sure that we're able to predict new walking motions where the ground contact pattern can change significantly. So what I'm going to do now is I'm going to talk about each of these 4 different areas from the toolbox and show how we'll put these elements together. So the first area is predictive gait optimization, and so this is some work that we've done in the past where we have a 27 degree of freedom full body walking model. It's 3-dimensional, and we go through an optimization calibration process to figure out where to put all the joints in the body in the model so that the model can follow experimental marker motions collected in the gait lab very, very closely. We also go through a calibration process in the mass distribution of the body, and so at the end of the day, we end up with a model whose mass properties and joint locations are similar to the individual subject being studied. And so here's a nice animation that Jeff Breinbolt made as part of his dissertation. And in the blue circles, we have experimental marker locations that were measured with the motion capture system. And the red dots are locations of the markers on the same model, except the model now has joints in it. We have a ball and socket joint for the hips, and a pin joint for the knees, and 2 non-intersecting pin joints for the ankles, and so forth. And you can see that that model can follow the experimental marker motion really, really closely, which is great. The one drawback is that the model is kinematically consistent, but it's actually not dynamically consistent, meaning that we have some fictitious, unwanted reaction forces and torques that act on the pelvis that aren't really there in real life when people walk. So we wanted to use this model to predict walking motions, and this was our first attempt at doing that. And of course, as you can see, this model is not doing a very good job of walking. He's falling over. And this is because we tried using forward dynamics initially, where we would guess joint torque controls and then use forward dynamics to predict the motion. And the problem, of course, is that we're extremely unstable. And so what we need to do optimization is we have to have stable simulations that can be repeated. We'd like the optimizations to be fast, just a matter of minutes, so that we can predict new walking motions. Initially, we didn't want to have a ground contact model just to make life easy, and we also wanted to predict new walking motions that would be realistic, so they wouldn't look funny in any way. And so the concessions that we made is, rather than doing forward dynamic optimization where we guess forces and then simulate motion, we decided to do inverse dynamic optimization where we guess motions and then calculate joint moments that would be required to produce those motions. We constrain the foot path to something that could be measured experimentally and then apply the experimentally measured ground reactions to the feet. We also let those vary a little bit, but we don't have any physics that relates how the feet interact to the ground. And then we have some nominal joint moments from inverse dynamics, and we're going to try to reproduce those with the model so that the muscles really wouldn't do anything that's too different from what they did experimentally. So we took this framework and we applied it to a subject who had medial compartment knee osteoarthritis, and our goal was to minimize an indicator of medial compartment knee load, which is the knee adduction moment, which really describes the medial lateral load split in the knee. And on this side over here, you can see our experimental walking motion. Here's what our optimization predicted. And again, the optimization is trying to produce a walking pattern that looks normal and minimizes the knee induction moment. And in fact, these two patterns look extremely similar. And yet the optimization was able to reduce the knee induction moment by 35% roughly. And we've tried this in the lab. It does work, though it's difficult to teach people to do it. But this gives us some hope that we can actually use computational methods to predict new walking patterns that could be of clinical value. So strengths and weaknesses here. So strengths of this approach is we can predict new gait patterns for which no experimental data are available. We have fast and stable simulations, and we're using patient-specific skeletal anatomy. But weaknesses, it's difficult to model new foot-ground contact patterns. We have non-physical residual loads acting on the pelvis, and we have no accounting for patient-specific neural control capabilities and limitations, which of course is important if we want to model individuals who have had a stroke. And then finally, motion smoothness is imposed on the solution because we're guessing joint motions in this process. Okay, so that's the first area in the toolbox. The second area is muscle synergy analysis, and a fun way to introduce this is to have a brief reading from Harry Potter and the Deathly Hallows. So shortly you will hear the recorded voices of Harry, played by my son Christopher, Hermione, played by my daughter Rachel, and Dumbledore, played by yours truly. And what we're going to do is we're going to take these three pre-recorded voices and we're going to mix them together linearly, and we're going to create 5 mixtures of the 3 voices. And so you can think of this as though the 3 of us were in the room together reading our parts at the same time, and there were 5 microphones across the ceiling in the room at different locations, and each microphone was recording a different mixture of our 3 voices. So you now have these 5 mixtures, and the question you want to answer is, how many people were speaking and what was each person saying? Can we decouple this? And I want to acknowledge Jeff Reinbolt here for this nice Matlab code that I'm about to show you. So we're going to run the Deathly Hallows program. All right, so here are our 3 original recorded voices that you can see visually.
Abby, is this Joe Cottage? Harry whispered, clutching the 2 lines he had brought from the math voice.
What are we going to do, though? Said Hermione finally, taking herself back to seriousness.
Master of Death, Harry. Master of Death. Was I better, ultimately, than Voldemort?
Okay, so there's our 3 voices. So now let's mix them together. Okay, we just mixed them. So here's our 5 mixtures of voices. So let's hear what those sound like.
Master of Death. Master of Death. Master of Death. Master of Death. Was I better, ultimately, than Voldemort? Master of Death. Master of Death. Master of Death. Was I better, ultimately, than Voldemort? Master of Death. Master of Death. Was I better, ultimately, than Voldemort?
You can really hear the difference in which voice comes through the most in each mixture. Okay, so now in real time, we're going to do something called independent component analysis to see if we can decouple the 5 signals. Done. That we actually did that. I didn't pre-compute that. And now we're going to play the recovered signals.
What are we going to do, though? Said Hermione finally, taking herself back to seriousness.
Abby, is this Joe Cottage? Harry whispered, clutching the 2 lines he had brought from the math voice. Master of Death, Harry. Master of Death. Was I better, ultimately, than Voldemort?
So I think of this as magic. It's pretty amazing that computationally we can recover the original 3 voices. And here are the 3 signals. And if you compare the 3 recovered signals to the original ones, you'll see that they look the same except for one thing, which is that the order has changed. There's nothing sacred about the order here. It's just mathematically recovering the original signals. So that's pretty cool, but what does that have to do with muscles? So if we come back to the presentation here, hopefully we come back to the presentation. It's trying to sync up again. Of course, this is the one thing you can't practice is doing it with WebEx. Let me try going down and back. Sorry, I'll have to get out for a second. Looks like we have a computer glitch. Oh, there we go. Whoops. Sorry about that, folks. There we go. Phew. Okay. So what this has to do with muscles is that if we think of having a whole bunch of EMG signals, mathematically we can show, just like our 5 recordings of voices, that these EMG signals are not independent from one another, that they can actually come from a smaller subset of signals. And we're going to give those signals a name. We're going to call them neural commands for the sake of discussion. And each of these signals is going to contribute to each muscle EMG signal. And the weights that describe how the individual neural commands contribute are going to be called synergy vectors in our terminology. And so if you have a single neural command and then the weights that describe how it contributes to each muscle EMG, we'll call that a muscle synergy. And if you want to see a good description of this, you can look at the Ting and Schwatal article in 2010 that describes how you can do these calculations to decompose muscle EMG signals into individual muscle synergies. So to show how this can be valuable, we collected some gait data in Carolynn's lab, over 200 gait cycles using an instrumented treadmill, full body motion capture, and 12 muscle EMG electrodes on each leg. And here's what the processed EMG signals look like. So they're rather reproducible from cycle to cycle, though you can see some variability. The solid lines are the average values, and the dotted lines are the standard deviations. So one of the things that you can do when you do the synergy analysis is you have to presuppose a certain number of synergies, and then you can see how well that number of synergies is able to reproduce the variability in all of the muscle EMG signals. So here, if we had only one synergy, so we had one basis function, if you will, or one neural command, we could actually reproduce 70% of the variability in all of those muscle EMG signals, which is pretty amazing. If we add a second neural command, a second synergy, we can get up to about 88% of all variability accounted for. If we add another one, go to 3, we're up to about 92%. And when you get to 4 synergies, we're now at 95% of the variability. And as we add more synergies, it just goes up a little bit. And for 12 muscles, we'll get to 100% variability when we get up to 12 synergies. So if we look at 4, since that's where we reach 95% variability accounted for, this is what the individual neural commands look like. So we have 4 time-varying signals. And these are the associated synergy vectors. And what these plots show is that if I wanted to reproduce, for example, gluteus maximus right here, I would take this time-varying signal and multiply it by this weight. And then I would take this the blue time-varying signal, multiply it by the blue weight there, the purple signal, multiply it by the purple weight, and then the gold signal, multiply it by the gold weight. And if I add those up, I'll reproduce most of the variability in the gluteus maximus signal. Now, Clark et al. In the Journal of Neurophysiology did a really interesting study where they looked at healthy individuals and individuals who've had a stroke, and I believe they were using 90% VAF as their cutoff. And what they found is that healthy individuals, or the non-predic side of individuals who had a stroke, would typically require 3 or 4 synergies to reach about 90% variability accounted for. However, if you look at the predic side in individuals who had a stroke, they would only need 2 or 3 synergies to reach 90% variability accounted for. So it was almost like they lost a basis function, or a building block, if you will, for constructing muscle excitation patterns. And so the message I want to make here is that muscle synergy results can be viewed as constraints on a patient's achievable neural control strategy, and it would be great if we can take advantage of that information somehow in simulating and predicting what a patient can achieve. So the strengths of synergy analysis: it provides dimensionality reduction for modeling neural control complexity. It can represent patient-specific neural control capabilities and limitations. The weaknesses is it's been primarily used for descriptive rather than predictive modeling purposes thus far. Rick Neptune's lab at UT Austin is doing some nice work in this area to use it for predictive purposes as well, but for the most part, it's just been descriptive. And it's also unknown how much any individual can change his or her neural commands and synergy vectors due to treatment. So that's going to be an important area to look into. So the third area in our toolbox, and this one is new, is something that we call statistical moment estimation. So if we think about constructing a musculoskeletal model, the traditional way to do it is we make a model, and the model has certain parameter values in it, and we assume that those parameter values are the same across all time frames, that they don't change, and that somehow the inputs to the model are going to change with time, but the parameter values don't change. What we're doing differently here is we're going to assume that parameter values are going to be constant, not across time, but at a particular normalized location and a motion cycle, which works well for gait because it's a very stereotypical sort of motion. But now in order to calculate parameter values, we're going to need to have a large number of motion cycles for each time frame. And so the difference here is instead of having one parameter set for all time frames, we're going to have a different parameter set for each time frame. And what this buys us is if you think about a traditional musculoskeletal model, you have all these model parameters that we see over here that you need to calibrate for every individual muscle in your model, and these parameters need to apply across all time. And that's a very difficult process to do, and it's difficult to show that these parameter values are correct and unique. Our statistical approach here is that at each point in time, we just have a regression model. We do have a nonlinear term at the front, but once we account for that with optimization, the rest of the problem is just a linear regression. And we apply this at each time frame, and we have a much smaller number of parameter values for every muscle. So if we go through the process of calibrating that statistical model to the walking data that I showed previously, what we find is that we're able to reproduce, this is the knee flexion extension moment, we can reproduce the experimental moment in black quite closely, and the calibrated result is in the blue curve here. And if we now take some of the walking trials that we didn't use in the calibration, we can see that the model predicts quite well also. And so this gives us reason to believe that if we can extend this to other joints, we'll have a really nice approach for going straight from processed EMG to muscle moments without having a real muscle model in between. One of the things to consider here is whether or not the predictions are physiologically consistent. I think we still have a little more work to do here, but in general they are. Flexor muscles, which we see in blue here, generally produce flexor moments. Extensor muscles in red generally produce extensor moments. And we don't have EMG from all muscles, so the reason that we may have a little bit of extensor moment coming from flexor muscles could either be a modeling issue or the fact that we're just missing some muscles from the model still. So the strengths of this approach is we don't have to have any musculoskeletal geometry to define muscle origins and assertions and moment arms and those sorts of things. We eliminate a large number of model parameters, and we get unique and computationally cheap solutions for linear model structures. Weaknesses we have, we need a large number of gait trials to create an overdetermined linear system of equations, and this approach will only work for stereotypical motions where time can be normalized. All right, and our last area is foot-ground contact modeling. So what we want to do here is we want to have models of foot-ground contact that are also customized to the way that a patient walks. And so what we're doing is we're creating a grid of springs on the bottom of the foot, so nothing new and exciting there. And we're using a nonlinear force model where we have a linear spring, but then we have nonlinear damping added on. Some people refer to this as a Hunt and Crossley model. And we go through an optimization process where we try to calibrate these spring parameters. We also have a friction model in here as well, so that every spring is going to have 3 components of force, a vertical force and 2 components of horizontal force. And we want to see if we can match all 3 components of ground reaction force measured from the force plate, the center of pressure in the 2 horizontal directions, and then the free torque in the vertical direction as well. And when we go through this optimization process, we end up predicting stiffness values of the springs across the bottom of the foot, and they're non-uniform. And at the end of the day, we can actually predict how the pressure across the bottom of the foot changes during stance phase of the walking motion. And if we look at what our calibrated ground reaction forces look like, here we have the anterior-posterior force, the vertical force, the medial-lateral force, and we can see that the calibrated model, which is in red, predicts the experimentally measured forces in blue extremely well. And if we now look at the center of pressure and the free torque, and the AP and medial lateral center of pressure, we can predict those extremely well. Can do a little bit better on the free torque, but not bad overall. So, so we're getting to the point now where we can predict all 6 components of ground reaction quite accurately for an individual subject for the type of shoe that we used for the calibration. It may be more difficult to do that for another shoe. So the strengths of this approach is now we have physics to model foot-ground interactions. If you recall before, we had to prescribe where the foot went ahead of time. Now we should be free to let the foot go wherever it will, and we'll let physics tell us how the foot interacts with the ground. This will facilitate prediction of new gait patterns with different foot paths and ground contact patterns. We don't need any special calibration trials. We're just using the gait data to do this. Some weaknesses, we have to outline the foot with a marker pointer to know where we should put the springs on the bottom of the foot. It may not work for other shoe types other than the ones that we used in this case. And here we chose Adidas Samba sneakers, not just because I like them, but because they have a nice flat bottom to them that makes them really easy to use for this purpose. And we do have to do some optimization to calibrate the shoe geometry and spring parameter values to a patient's gait data. Now the last point I'm going to make here is integration. We have to take all of these different things and somehow combine them. And the framework that we've taken from this is some nice work done in Daryl Thalen's lab, where he created something called the residual elimination algorithm. And it's a way of producing forward dynamic simulations that are stable and match experimental data well. And so we've modified this a bit, and we're going to use it to do predictive gait optimization, where we're going to predict new walking motions, not just ones that we have experimental data for. It gives us stable forward dynamic simulations, which is a requirement to be able to do forward dynamic optimization with it. We will now have physics-based foot-ground contact models, and muscle synergies will constrain the joint moments that the model is capable of producing. So here's an example of our modified REA approach in this animation. And again, the experimental markers are in blue, and the model markers are in red. And you'll see that the model doesn't match the experimental markers as well as the previous case did. What we've done here is we've given up a little bit of kinematic consistency in order to have 100% dynamic consistency. So we now have no residual loads on the pelvis in this model. And really, our goal here is that we want the neuromechanical limitations that we have in the model as defined through the synergy analysis to define the biomechanical limitations of how the patient can walk. So in terms of how we hope to use this in the treatment design process, we want to analyze pre-treatment muscle synergies to define the achievable variations for an individual patient. And then we would perform a predictive gait optimization to predict a theoretically best achievable gait pattern for the individual patient. And then finally, we would use the predicted changes to inform patient-specific treatment design. Now, how could we do all of this in OpenSim? So what I should mention here is that all of this work, this is all developmental, so this is still in progress, but all of this work we've done in Matlab so far. And it would be great if we could move this into OpenSim so that at the end of the day, we could roll it out and other people could use it, other labs could use it, and it would become a clinically useful tool. So a recent addition in OpenSim 3.0 is you can now use Matlab optimization to drive OpenSim models through new scripting capabilities. And so muscle synergy analysis that we have at the top here, along with statistical moment estimation, those could be combined into an OpenSim plugin so that both of those tasks could be performed easily in OpenSim. Down here, we have the residual elimination algorithm that we do in Matlab, and that could likely be replaced with the OpenSim residual reduction algorithm to do more or less the same thing. And then finally, our foot-ground contact model at the bottom, that could also likely become an OpenSim plugin so that all of these modeling steps could be done in OpenSim, and we could still allow Matlab to be the optimization driver.
Okay, well, thanks, BJ, for pulling that all together. And we just will make a couple of closing remarks to talk about where this might go between the clinical and the technical worlds, and propose that what we want to propose is a paradigm shift for model-based rehabilitation, and that is using the simulation tools or using the modeling tools, being able to predict what is possible, what is an individual patient's capacity for improvement. This could be done mathematically, and if this could be done non-invasively ahead of time, we would really be informed on how to deliver more effective interventions. Second point is that based on the synergy analysis and the neural control strategies, what can change in those parameters can inform what can change biomechanically and help us to identify predicted change, biomechanical changes to be the targets, the specific targets for the treatment interventions. Of course, we have to end with the major caveat that the approach is a work in progress, but BJ and I have been discussing this for a couple of years now, and as it iterates, we become the ideas become more refined and more sophisticated, and we actually get a sense of how to solve these problems. But indeed, it is a work in progress. But our job is to be doing research. So we're going to end there. Not, of course, without thanking the people who support our work. At the moment, we have a project together funded from the National Science Foundation. The experimental and clinical work that I presented has been funded by the Department of Veterans Affairs. And many of the components of the toolbox and the developmental work behind the modeling has been supported by BJ's R01. So thank you for your attention.
Okay, back to you, Jen.
All right, thank you both for a great talk. Let's dive right into the Q&A sessions. All the questions will be text-based, so go ahead and find the Q&A panel in your WebEx controls and type in your question. Make sure you select to ask all panelists. And with that, go ahead and type in your questions. While we're waiting for some audience questions to come in, I'll start off with one. So I'm not super familiar with muscle synergies, but I'm wondering what the effect of noise is on the muscle synergies that you discover. I guess what I'm thinking or wondering is if there's more noise in the signal, which you might suspect would be the case in patients with stroke, are you less likely to discover, are you more likely to discover fewer synergies?
So Jen, if I could ask a little clarification on that. When you talk about noise, do you mean physiologic noise, just variability?
Yeah. Mm-hmm.
Yeah. I actually think that's one of the strengths of the synergy analysis, if you will, is you're looking for what emerges out of the concatenated signals. And many of us these days are collecting data with multiple cycles of people walking on a treadmill, and so you end up with enormous data sets. And that's been a huge boon to the synergy analysis. But so on the one part, that there's not that specifically addressing people with stroke, and is there more physiologic noise in their EMG, and is it harder to get things? No, I think it's the quality of the data that you get. If you collect good data, then you have perfectly usable EMG signals. Are there fewer synergies? It seems to be the case. Depending on how you constrain your synergy analysis, there are people who have discovered fewer synergies in the predictive. But that seems to be very clearly related to the control strategy, not to the quality of the signal.
Okay, thanks. So come on, audience, ask us your questions. But again, while we're waiting, I'll ask another question. Oh, here we go. We do have an audience question, so I'll go ahead and ask that one. So this is from James Finley. Is the primary advantage of using synergy analysis as opposed to the data from individual muscles, is the primary advantage to reduce the complexity of the optimization?
Yes. So, what's so cool about the synergies is that it tells us, if we measured 20 EMG signals in one leg, that those 20 signals aren't really independent from one another. There were maybe 3 or 4 or 5 independent signals that could be used to reconstruct those 20 signals. And so what that means is that people, when they walk, don't just create any random combination of 20 signals as their muscle excitation patterns. There are really some sort of limitations on what people achieve, and we can quantify that with synergies. And so then the question becomes, when you do the synergy analysis, what aspects of what you calculate can be changed by the individual? And certainly the neural commands can be changed as people walk. Those are time-varying signals that can be changed. What's a little less clear is how constant the synergy vectors are and how much those change from cycle to cycle or across different types of walking patterns, different speeds. And so those sorts of questions are things that are open to investigation. So I think there's a lot of room for growth and study in this area, and I think it's going to be really useful as an additional constraint that we can take advantage of in musculoskeletal modeling.
Okay, now we have another question from, this is from Tim Dorn here at Stanford. What objective function do you plan to use in the optimization to achieve a realistic walking motion?
So we have 2 things that we've thought of doing. One is targeting a particular gait speed so that we'll force the model to speed up. And then the other thing is we want to create some sort of objective function related to bilateral symmetry. So differences in joint angles between the 2 sides, of course, time shifted half a cycle. So that's currently what we're planning to use. And then the constraint is going to be you can only produce muscle excitations that can be achieved using muscle synergies. So for example, we could assume that the person's synergy vectors can't change, so we need to look at the data and see if we think that's a good assumption, and that maybe the neural commands can change. So if we have, say, 3 neural commands on one side and 5 neural commands on the other, we can only construct muscle excitations that are within that box, if you will. And what optimization solution will the model find if we tell the model, okay, walk twice as fast and try to produce a walking motion that is close to being symmetric bilaterally?
That actually leads into the question I was going to ask a couple minutes ago. So I'm really interested in the interplay between the clinical and experimental work and your the modeling and simulation work. Are there other ways that the past clinical work, whether it's Carolynn's work or other people's investigations, is going to drive the first type of variables you look at changing, or where you're going to start, what your hypotheses are on the modeling and simulation side? Are there other examples?
Well, the one thing I can comment on from Carolynn's work is the whole responder, non-responder data set is really a wonderful data set, because here we have people that did have some level of response, and we can look at what did they change in their synergy. Something must have changed because they walked better. And what about the non-responders? Did they get any change as well, or did they stay relatively constant in terms of their synergies? And so as we work with that data set just at the level of synergy analysis, our hope is that we'll get a better handle on what sorts of things patients can change in their synergies. And then that's going to inform what we can put into the model in terms of things to manipulate in the model. I don't know if we have other examples, though, of... Yeah. Can you clarify that question a little bit more?
Well, I guess there's a big space of different gait patterns that someone could adopt. Are there any differences seen between the responders and non-responders that you could look in that, change your objective function to try to get those kinematics and see if it bears out in the simulation as well?
Yeah, so certainly we can tie the predictions back to the Carolynn's clinical data. So once we start generating predictions, say we predict that someone could walk twice as fast, and we looked at what changes, and at that point we may see certain changes that the model identified that may be consistent with a certain category of responder. And so if that happened, that would tell us, aha, this person looks like they fit into the clinic-based gait training category based on what the model predicted, and so it may be really valuable to take them down that path. And in fact, here are some suggestions from the model for where to focus that intervention. Or the model may predict a change in gait pattern that looks a lot like the things that would characterize someone that responded to the power intervention. And so that then might tell us, aha, this individual might be a really good candidate for the power intervention, but not such a good candidate for the clinic-based gait training intervention. So we will be trying to tie the model predictions back to what we saw in these different categories of patients, so that we can then use what the model predicts to hopefully inform which treatment path to go down.
Okay, I think we'll have time for one more question. So Ala, I think he didn't get his full last name in, but the question is just asking for a little bit more detail about the muscle synergy analysis. I think he's wondering how many muscle activations you're looking at, whether you're trying to tease out several muscle activities from a single EMG signal or multiple EMG signals.
So the whole point of the synergy analysis is that we start with multiple EMG signals. So in the example that we showed in the presentation, we had 12 EMG signals from each leg. And the assumption of the synergy analysis is that those 12 EMG signals are not mutually independent from one another, that there is a smaller subset of signals, which we term neural commands, that can be linearly combined to reconstruct the experimental EMG signals. So the experimental EMG signals get normalized, and once they're normalized, we now want to see if we can mathematically, just like in the Deathly Hallows example, if we can mathematically figure out if there was a smaller number of independent signals that could have potentially been used by the human neural control system to construct that larger number of EMG signals. So we're just looking for dependencies in there and trying to find reduced descriptions and reduced complexity of the experimental EMG data.
Okay.
Yeah, I actually referred that individual to the Ting and Schwartel article, 2010, and also the Clark article on looking at individuals who had a stroke. Those articles do a nice job of explaining how the whole synergy process works.
Okay, actually we'll do one more quick question about the statistical moment estimation. This is a question from Matt Demers. So if he understands it correctly, the model can change through time. Its set of parameters can change over the course of the motion. That's correct, right?
Exactly. The parameters change over the course of the motion.
So how variable are the parameters throughout the gait cycle?
The person doing that work sitting right next to me, I'm going to ask him.
Well, we have to constrain them in order for them to be realistic. If we allow it to vary freely, we can actually match the moment perfectly, like 0.99 R squared, very, very low RMS, but we'll get highly variable parameters throughout the cycle, which is just not physiological. So recently we've been constraining them using a Pauli Fourier series, and we're also looking at using a nonlinear B-spline to match the, or to constrain how these parameters can vary throughout the gait cycle to try to get them to vary smoothly. In general, they'll actually vary pretty smoothly even if we use high order Pauli Fourier series. However, there's a few that might vary very highly throughout the gait cycle.
So we are imposing a little bit of smoothness across the cycle just so that things don't jump around from one time frame to the next.
Right, that makes sense. Okay, I think with that, we'll go ahead and close this webinar session. There were a couple questions we didn't have a chance to get to, but as long as it's okay with you guys, I can put them in touch with you, BJ and Carolyn.
Sure, that's fine.
Yeah, so if you can go on to the next slide for me. Okay, so we also, I also want to acknowledge our funding sources for the OpenSim project and the webinar series. We're supported by a couple grants from the NIH, as well as a grant from the European Union, and by the, we're also supported by the DARPA Warrior Web project. I want to thank all of you for a great discussion. Can you go on to the next slide?
Next one beyond that.
Oh, so there you can see our funding sources again.
There you go.
Oh, no, next one.
Sorry about that.
Yep, there we go. So again, thank you all for a great discussion. If we didn't get to your questions, I'll put you in touch with BJ and Carolyn. Please check out our website for information about upcoming events. We'll have another webinar the beginning of December from the NMS Physio team that's developing image-based model building software. That's a webinar, I think it's December 4th, but we'll have information about that on our website. You can also find recordings of, we'll post a recording of this webinar and past webinars as well. You also get a survey that will appear in the pop-up window. Please fill that out to give us some feedback. So with that, thank you all for participating. I hope you'll tune into future webinars and stay involved with the OpenSim project.